welcome to the Joy of Architecture. Today we're diving deep into the fascinating, ever-evolving world of modern database technologies.
It really is evolving fast. So many options out there now.
Exactly. And if you've ever felt a bit overwhelmed by all those choices, or just wondered why a simple database seems so complex these days, then, well, this deep dive is definitely for you.
Yeah, our goal here is really to give you a clearer map of this landscape. We want to help you understand the crucial trade-offs and maybe some of the surprising innovations driving things.
We'll look at the different paradigms, starting with the familiar relational systems, but also venturing into the newer frontiers of specialized databases.
And we'll unpack their unique architectures, their strengths, and crucially, the specific problems they're actually designed to solve.
Okay, let's kick things off with the enduring power of relational databases. SQL databases, as many know them. This is sort of the bedrock, isn't it? Started with Edgar Cod back in 1970.
Absolutely. Before COD, things were, well, pretty messy. Hierarchical, network databases, complex stuff. His big idea was simple but revolutionary. Organize data into tables, relations with rows and columns.
Made things logical.
Totally. And define relationships using primary and foreign keys. But the absolute core, the defining characteristic, is acidity transactions.
Right. Atomicity, consistency, isolation, durability. You hear that acronym all the time.
And for good reason. It's the foundation for data integrity. It guarantees your data stays valid, stays correct, even if, the power goes out or the server crashes mid-operation.
Which is why there's still the standard for anything like financial systems, e-commerce checkouts, basically anywhere you absolutely cannot lose or corrupt data.
Precisely. It's essential for those OLTP, online transaction processing workloads.
So for our relational deep dive, let's look at PostgreSQL, or just Postgres. It's a really advanced open source favorite. How does it work inside?
Okay, Postgres has a process-based architecture. There's a main postmaster daemon, and when a client connects, it forks off a separate backend process just for that connection.
Ah, so one process per connection. That sounds like strong isolation.
It is. It means if one connection does something crazy or crashes, it's unlikely to take down the whole database, data itself. Stored in what are called heap files, usually split into 8 KB pages in a row-oriented format. Good for general-purpose queries.
Got it. Row-oriented.
Yeah.
And indexing. How does it find data fast?
Postgres has a bunch of index types. The default, most common one is the B-tree index. Great for equals, greater than, less than type queries.
Standard stuff.
Yeah, but important to know, all indexes in Postgres are secondary indexes. They store the index value and a pointer back to the actual row data. But it also has specialized indexes like gist and gene.
Okay, what do you wait for?
Gist and gene are really powerful for things like indexing JSON-B data or doing full text search. And then there's Brin, which is optimized for huge tables where the data has some natural physical ordering.
Interesting. So different tools for different data shapes. Now, how does Postgres decide which index to use or whether to just scan the whole table?
That's the magic of the cost-based optimizer. When you send a query, it doesn't just run it. It figures out multiple ways it could run it.
Like, should I use index A, index B, or just read everything?
Exactly. And different ways to join tables, too. Nested loop, merge join, hash join. It estimates the costs, CPU, disk I/O for each plan, and picks the cheapest one.
And that's where Explain comes in handy for developers, right? To see what the optimizer chose.
Oh, absolutely invaluable. If a query is slow, Explain is your first stop to understand why.
Okay, crucial topic, concurrency. Lots of users hitting the database at once. How does Postgres handle that without people tripping over each other or seeing half-finished updates?
That's MVCC, multi-version concurrency control, and it is really cool. The basic idea is readers never block writers, and writers never block readers.
How does that work?
When you update a row, Postgres doesn't just overwrite the old data. It creates a new version of the row. Each version gets tagged with transaction IDs. So when your transaction starts, you see a consistent snapshot of the data as it was at that moment, unaffected by writes happening concurrently.
Ah, like time travel for data.
Kind of. And then a background process, auto-vacuum, comes along later and cleans up the old, no longer visible row versions. Postgres even offers serializable snapshot isolation, or SSI, for the absolute strictest level of consistency if you need it.
That's pretty sophisticated. What about scaling, if one server isn't enough?
Well, the traditional route is vertical scaling, bigger machine, more RAM, faster disks. But for horizontal scaling, spreading across multiple machines, Postgres has options now.
Like what?
There's native declarative partitioning to break up huge tables within a single node, which helps performance. But for true distribution across multiple servers, you often use extensions like Citus.
Citus, what does that do?
Citus essentially transforms a cluster of independent Postgres instances into what looks like a single massive distributed database. It handles sharding the data and routing the queries for you.
So it makes Postgres scale out more like a NoSQL system in some ways. What about just keeping it running? High availability.
That's typically done with replication. Streaming replication is common. The primary server streams its transaction log, the GUAL, to one or more standby servers.
Real-time copies.
Pretty close to it. It can be asynchronous fast, but potential for tiny data loss if the primary crashes instantly or synchronous, which guarantees zero data loss but adds a bit of latency to writes. Standbys can also serve read-only queries, which helps scale reads.
And there's logical replication too.
Yep, logical replication is more selective. You can replicate specific tables, maybe even between different Postgres versions, or to other systems entirely. It works at a higher level than just streaming the raw log files.
But managing all this failover, if the primary dies, balancing connections Postgres doesn't do that itself, does it?
No, not automatically out of the box. You typically bring in external tools. Bouncer is very common for connection pooling, managing all those back-end processes. HEProxy can load balance read traffic across replicas, and something like Patroni manages the cluster state and handles automatic failover, usually using a consensus store like etc. or console to make sure nodes agree on who the leader is.
Right, avoiding that split brain problem. So this brings us to CAP theorem territory. Consistency, availability, partition tolerance. Pick two, usually. Where does Postgres fit?
A single Postgres node is CA consistent and available. Once you distribute it with replication, it depends. Synchronous replication makes it CP. You prioritize consistency over availability during a network partition. Asynchronous replication leans AP. You prioritize availability, accepting a small risk of data loss if the primary fails before a write replicates.
Okay, so summing up Postgres. Strengths are immense data integrity via AC, great extensibility like PostGIS for maps, full SQL compliance, huge community, a real powerhouse.
Definitely. Batteries included is a good way to put it, with things like JSON-B support built in.
Limitations. Maybe that process per connection overhead at massive scale, and needing extensions or tools for true horizontal write scaling.
Those are the main ones. The single primary node for writes in a standard setup is the key bottleneck for really extreme write loads.
Still, it's used everywhere. Primary system of record, web apps, geospatial, even data warehousing. Companies like Apple, Skype. It's incredibly versatile.
It really demonstrates that concept of polyglot persistence. Even if you use other specialized databases, a solid relational core like Postgres is often essential.
Right. But those limitations at massive scale, especially write scaling and global distribution, that's exactly what opened the door for the NoSQL movement, wasn't it?
Precisely. Around the mid-2000s, web companies were facing scales, data volume, user load, uptime requirements that traditional relational databases, scaling vertically, just couldn't handle cost-effectively.
So NoSQL, not only SQL, came along. What were the core principles?
Primarily, horizontal scalability built in, distribution first, flexibility. Often this came at the cost of the strict ACE-D consistency we just talked about.
Back to the HEP theorem again.
Exactly. Most NoSQL systems lean towards AP available and partition tolerant. They often operate under a base consistency model. Basically, available, soft state, eventual consistency. Meaning the system is generally available, its state might change over time without input, soft state, and data will eventually become consistent across all replicas, but maybe not immediately after a write.
And NoSQL isn't one single thing. It's like a family of database types.
Correct. You've got document stores like MongoDB, key value stores like Redis, wide column stores like Cassandra, and graph databases like Neo4j. Each optimized for different data shapes and access patterns.
Okay, let's start with document databases. MongoDB is probably the best-known example. Developers seem to love its flexibility.
They often do. It uses a flexible document model, storing data in JSON-like BSON format grouped into collections. The big win is often denormalization. You can embed related data right inside a single document.
So instead of joining tables, you fetch one document and get everything.
Exactly. That dramatically speeds up reads for common access patterns. It's often called schema on read. You don't need a rigid schema up front, making development iterations faster. Under the hood, it uses the wired Tiger storage engine, which gives it document-level locking, compression, and caching.
Flexibility sounds great. How about querying and Crucially, transactions, consistency.
MongoDB has its own query language, MQL, which is JSON-based, and a pretty powerful aggregation pipeline for complex data processing. Historically, atomicity was only guaranteed at the single document level.
But that changed.
Yeah. Yes, big change. Since version 4.0, MongoDB supports multi-document ACID transactions. This was huge, allowing strongly consistent operations across multiple documents, collections, even shards.
That really broadened its appeal for more critical workloads. How does it handle scaling out and staying available?
Availability comes from replica sets. You have a primary node taking writes and secondary nodes replicating that data. If the primary fails, the secondaries hold an election and promote a new primary. This also allows you to scale reads by directing queries to secondaries.
And for scaling writes beyond one primary?
That's sharding. You partition your data across multiple shard replica sets based on a chosen shard key. Clients talk to Mongo's routers, which figure out which shards have the data for a given query.
Okay, so AP-wise, where does Mongo usually sit?
For writes within a replica set, it typically acts as CP prioritizing consistency during elections. But you have read preferences that let you choose whether to read from the primary for strong consistency or from secondaries for potentially slightly stale, eventually consistent data, but maybe lower latency or higher read throughput.
So strengths, flexible schema, built-in scaling in HA, rich queries, mature ecosystem, especially with their Atlas Cloud service. Downsides.
The main one is still no complex joins. You really need to design your schema with denormalization in mind. Multi-document transactions add some overhead. And managing a large, self-hosted, sharded cluster isn't trivial.
But used widely, Adobe, Uber, Google for things like content management, user profiles, real-time analytics. A very popular choice.
Definitely, especially where developer velocity and schema flexibility are key.
All right, shifting gears from documents to something built for absolutely massive write volumes and always-on availability. Wide column stores. Apache Cassandra is the prime example here.
Yes, Cassandra is designed for scenarios where downtime is simply not an option, and you need to ingest huge amounts of data very, very quickly. Think IoT data streams, messaging platforms, activity logs.
And its architecture is fundamentally different, right? Masterless.
Completely. It has a masterless peer-to-peer architecture. Every node in the cluster is identical. There's no single point of failure, no master node bottleneck. Data is organized into key spaces and tables, but its wide column rows don't need to have the same set of columns. The primary key is crucial, composed of a partition key determining which nodes store the data and optional clustering columns defining sort order within a partition.
And data modeling is different too. You mentioned query-driven.
Very much so. Because Cassandra doesn't support joins, you design your tables specifically for the queries you intend to run. This often means significant denormalization, storing the same piece of data in multiple tables, shaped differently for different query patterns.
That sounds like it requires careful planning up front. What makes it so fast for writes?
That's the LSM tree storage engine log structured merge tree. Writes go to an in-memory mem table and are appended to a commit log on disk for durability. Then, periodically, the mem table is flushed to immutable SS tables on disk. It's all sequential appends, very fast. Reads might need to check the mem table and multiple SS tables, which is why reads can sometimes be slower than writes.
And compaction cleans things up.
Right, background compaction merges SS tables, removes deleted data marked with tombstones, and optimizes the structure for reads over time. Indexing is more limited. Secondary indexes work best on low cardinality columns, though newer SAI storage-attached indexing helps.
Query language, SQL-like again.
It uses CQL, Cassandra Query Language. Looks like SQL, but no joins, no subqueries, limited aggregations. Queries generally need to specify the partition key to be efficient. Transactions are atomic only at the single partition level. There are lightweight transactions, LWTs, for conditional updates using Paxos, but they have a performance hit.
Okay, that masterless design sounds incredibly resilient. How does it distribute data and handle consistency?
Data is distributed across the cluster ring using consistent hashing. You define a replication factor, RF, say 3, meaning every piece of data is copied to 3 nodes. The snitch helps place these replicas intelligently across different racks or data centers for fault tolerance. Nodes use a gossip protocol to discover each other and share cluster state.
And CAP. Sounds like availability is king here.
Absolutely. Cassandra is a classic AP system, but its killer feature is tunable consistency. For every single read or write, you can specify the consistency level, CL. Want a fast write? Write to 1. Need strong consistency? Read and write at quorum, a majority of replicas. You can guarantee strong consistency if your read CL R plus your write CL delta W is greater than your replication factor RF.
Wow, that puts a lot of control and responsibility in the developer's hands.
It does. You constantly trade off consistency guarantees versus latency and availability based on the specific needs of each operation.
So strengths. Extreme HA, linear write scalability, multi-data center mastery, that tunable consistency. Limitations. Constrained query model, eventual consistency requires careful thought. Reads can be slower, managing tombstone.
Pretty much sums it up. It's why companies like Netflix and Apple use it for things like viewing history, device state, messaging systems, massive scale, always on.
Okay, let's speed things up even more. Key value stores, focusing on Redis, often pegged as just a cache, but it's more, right?
Way more. Redis stands for Remote Dictionary Server. Yes, it's a key value store, but it's better described as a data structure server. The values aren't just blobs of data. They can be rich server-side data structures. Lists, sets, sorted sets, great for leaderboards, hashes, streams like Kafka-lite, geospatial indexes, even vector sets for AI embeddings now.
So you can do complex operations server-side.
Exactly. Push computation to the data. This reduces network traffic and application complexity. And the reason it's so blazingly fast, it's primarily an in-memory database.
All baby in RAM.
By default, yes, that's the source of its incredibly low latency. For durability, you have options. RDB snapshots, point-in-time dumps, or AOF appending every command to a log. Architecturally, it uses a single-threaded event loop.
Single-threaded, how does that scale?
It simplifies things immensely, makes command execution atomic, but it also means a single slow command can block everything else. So you need to be mindful of command complexity. Modern Redis does have background threads for I/O and certain tasks now, though.
How about transactions and scaling Redis itself?
Basic transactions using multi-XX. UQ commands, they run atomically, but no rollbacks if one fails midway. Watchit provides optimistic locking. For scaling, it's typically master replication, asynchronous usually for speed. Redis Sentinel handles monitoring and automatic failover. And Redis Cluster provides automatic sharding, splitting the key space across multiple master nodes using hash slots.
So generally an AP system again. Fast, available, but async replication means a tiny window for data loss on failure.
Correct. Though you can use the wait command to force synchronous replication for specific critical writes if needed. The main limitations are really that dataset size is limited by RAM, which can get expensive, and you need to manage that single-threaded nature carefully.
But yeah, for caching, it's king. Also session stores, leaderboards, rate limiting, pub sub, message queues. It's incredibly versatile and widely used.
A cornerstone of many modern web architectures.
Okay, now for something completely different, graph databases. Neo4j is the leader here. This is all about the connections, right?
Exactly. Relational databases store relationships implicitly via foreign keys. Graph databases make relationships first-class citizens. Neo4j uses the labeled property graph model, nodes, entities, relationships, directed connections, which can also have properties, and labels, like types for nodes.
What makes them fast for relationship-heavy queries, like finding friends of friends?
The secret sauce is native graph storage with index-free adjacency. This means each node physically points directly to its adjacent nodes and relationships in memory or on disk. Traversing from one node to its neighbor is effectively a pointer lookup, incredibly fast constant time, O1, regardless of the total graph size. Compare that to recursive joins in SQL, which get slower as the dataset grows.
So traversing the graph is inherently fast. Do they still use indexes?
Yes, but mainly for finding the starting points for a traversal. Neo4j uses standard indexes, btree, text, spatial, vector, on node properties to quickly locate, say, a specific user node before starting to explore their connections. The query language is Cypher.
Cypher. What's that like?
It's declarative, pattern matching. Uses this cool ASCII art style to describe the graph patterns you're looking for, like actor.person.actedinmovie.movie. Makes complex graph queries surprisingly intuitive to write and read.
One really interesting thing about Neo4j is that, unlike many NoSQL options, it offers full ACID compliance.
Yes, that's a major differentiator. It provides the transactional guarantees of relational systems, but optimized for graph data. For scaling in HA, it uses causal clustering. You have core servers that handle reads and writes, using the Raft consensus protocol to ensure consistency. You can add optional read replicas for scaling read queries.
So Raft consensus means it's a CP system, prioritizing consistency.
Correct. It guarantees consistency, specifically causal consistency, ensuring you read your own writes and observe events in a causally related order. For horizontal write scaling across multiple graphs, they've introduced Fabric.
Strengths: unbeatable performance for connected data traversals, intuitive model, ACD guarantees, expressive cipher language. Limitations:
It's not designed for huge analytical queries that need to scan all nodes or relationships. That doesn't leverage the traversal advantage. Horizontal write scaling with Fabric is newer and adds complexity.
but for things like fraud detection, finding rings, recommendation engines, people who bought this also bought, knowledge graphs for AI, identity management, network diagrams, it's incredibly powerful.
Anywhere the relationships are the key insight, Neo4j shines.
This journey leads us naturally to NewSQL. This category seems to be aiming for the holy grail, the horizontal scale of NoSQL with the strong ACD guarantees of relational databases.
That's exactly the goal. NewSQL databases emerged because there was a clear need for systems that could handle massive transaction volumes, globally distributed, but without sacrificing the strong consistency required for mission-critical applications like finance or global inventory. They are essentially modern relational systems architected for distribution from the ground up.
And our prime example is Google Spanner. Globally distributed, strongly consistent, relational. That sounds almost impossible.
It was considered nearly impossible for a long time. Spanner, originally developed inside Google and now a cloud service, really pushed the boundaries. It automatically shards data into manageable pieces called splits across potentially thousands of servers worldwide. It decouples compute and storage and provides a standard relational model with SQL.
Okay, but how do they achieve strong consistency across the globe? That's the hard part.
The absolute linchpin is Google's TrueTime API. This isn't just NTP, it's a highly specialized service using GPS receivers and atomic clocks in Google's data centers to give every server a globally synchronized time, but crucially, as an interval earliest, latest with very small bounded uncertainty.
Time is an interval. Why?
Because it allows Spanner to assign globally meaningful, unique, and monotonically increasing commit timestamps to transactions across all regions. By knowing the uncertainty interval, it can guarantee transaction ordering globally. This, combined with standard techniques like two-phase commit, 2PC for distributed transactions, and strict two-phase locking, allows it to provide external consistency, the strongest form of serializability. It knows transaction A definitely finished before transaction B started, everywhere.
So TrueTime basically provides a global ordering mechanism that drastically simplifies distributed consensus.
Precisely. It was a masterstroke. It also uses MVCC like Postgres for non-blocking snapshot reads. For replication, it uses Paxos consensus to synchronously replicate each split across multiple geographic locations.
What does this mean for scalability and availability?
Virtually limitless horizontal scalability for reads and writes. Compute capacity can be auto-scaled. Availability is extremely high, up to 99.999%, 5 nines, because it can survive entire region failures thanks to that synchronous multi-region replication.
And CAP sounds strongly CP.
Unequivocally CP. Consistency is paramount. Google argues it's effectively CA because their internal network and infrastructure make partitions incredibly rare, but fundamentally it will choose consistency if a partition occurs.
So the dream combination. Global scale, strong consistency, SQL interface. What's the catch?
It's proprietary, tied to Google Cloud because it relies on that specialized TrueTime hardware. It's also significantly more expensive than many other databases. And write latency can be higher, especially across regions, due to the synchronous replication and consensus involved.
For global finance, massive multiplayer games like Pokemon Go, global inventory systems, it solves problems few other databases can. A true NewSQL achievement.
It really represents the paceification of incredibly complex distributed systems tech, making it accessible.
Beyond these broad categories, we have a whole range of specialized databases. Let's quickly touch on a few time series databases like InfluxDB.
Optimized specifically for timestamp data. Metrics, events, sensor readings, high ingestion rates, efficient storage for time-based data, and query languages tailored for time window analysis are key. InfluxDB uses a point data model measurement, tags, index metadata, fields, values, and the crucial timestamp.
And didn't InfluxDB just get a big architectural overhaul?
Yes, InfluxDB 3.0 IOBIX is a rewrite using Apache Arrow and Apache Parquet, decoupling compute and storage, moving towards a more cloud-native model, and importantly, adding native SQL support alongside its traditional InfluxQL and Flux languages.
How does it scale?
Data is organized into shard groups based on time, tied to retention policies for automatic data expiration. Big caveat, the open source version lacks native clustering HA. You need the enterprise or cloud versions for true distributed scalability and fault tolerance.
So great for monitoring IoT, finance data. Specialized and OSS users need to manage HA themselves.
Exactly.
Next, search databases Elasticsearch.
Built for full-text search and analytics on semi-structured data. Think log analysis, website search, application monitoring. Core component is the inverted index mapping terms to documents, powered by Apache Lucene. Uses analyzers for text processing and BM25 for relevance scoring.
Document-oriented, JSON, REST API, Query DSL, but no ACID.
Correct. Atomic at the document level uses optimistic concurrency. Highly scalable via sharding indices across nodes with replicas for HA and read scaling, generally AP with eventual consistency.
Strengths are search speed, relevance, scalability, and its powerful aggregation framework for analytics, increasingly used for vector search in AI too.
Absolutely. The Elastic Stack, Elasticsearch, Logstash, Kibana is a standard for observability.
Then there's the radical world of blockchain databases, like Ethereum or Hyperledger Fabric.
Totally different paradigm. Distributed, immutable, append-only ledgers secured by cryptography and network consensus, like proof of stake or proof of work. No central admin. Smart contracts enable decentralized applications, dApps.
Ethereum is the big public one for DeFi, NFTs.
Right, permissionless. Hyperledger Fabric its permission for enterprise consortia, supply chains, etc., offering more control and privacy features like channels.
Strengths are trust, transparency, immutability without a central party.
Downsides.
Lower performance, higher latency, less storage efficiency, append-only nature limits use cases, high complexity.
And finally, embedded databases like SQL.
The hidden giant runs inside the application as a library. Database is just a single file. Serverless, zero config, full AC transactions, incredibly reliable and portable.
Perfect for mobile apps, IoT devices, desktop apps, but not for high concurrency network access.
Exactly. It's the most widely deployed database engine, period.
Wow, what a landscape. From solid relational foundations with Postgres, flexible NoSQL like Mongo and Cassandra, lightning-fast Redis, connected Neo4j, globally consistent spanner, specialized InfluxDB and Elasticsearch, trustless blockchains, to tiny SQL. It really underscores that there's no single best database. It's about trade-offs. Relational gives you consistency up front, schema on write. Some NoSQL gives flexibility, schema on read, but pushes validation to the app. Cassandra demands query-driven modeling. Tunable consistency puts the key AP choice directly on you.
And the rise of managed services, DBaaS, cloud-native options like Spanner or MongoDB Atlas, it feels like the operational complexity is being abstracted away more and more.
Definitely. It lowers the barrier to using these powerful but complex distributed systems. The focus shifts back to the application logic.
And emerging trends. Vector databases are huge now for AI, right?
Absolutely. Vector databases or vector capabilities added to existing ones like Elasticsearch and Redis are critical for semantic search, RAG, and other AI workloads. It reinforces the idea of multi-model databases and polyglot persistence. You use the best tool or combination of tools for the job.
So understanding these architectures, these trade-offs, that really is the joy of architecture. It lets you make informed choices.
It empowers you to build better systems.
So, as you tackle your next data challenge, maybe the question isn't, what's the one ultimate database? But rather, how do I intelligently combine the right databases to solve my specific problems? Something to think about.
Thank you for joining us on this deep dive into modern database technologies.
And if you found this insightful, please subscribe to Joy of Architecture for more explorations into the building blocks of our digital world.